Algorithms of iterations of distribution of subtasks between S-bots in one swarm-bot system. We are living through the rising complexity of existing and novel swarm-bot systems. There's applications in defense manufacturing, green energy, robotics, and other fields. They have new and more varied sources of information, intelligent embedded systems of control, and they face new environmental factors, larger numbers of constituent elements and internal collections, and therefore more complex structures, functions, behaviors, and greater modeling and scaling requirements. New swarm-bot systems' functions, parameters, structures, and behaviors can change over their life cycle, based on internal or external factors in the software or hardware. The goal of this project is to investigate the use of a central particle swarm algorithm that delegates subtasks between the S-bots of one swarm-bot system. Now, a group of mobile S-bots that acts collectively is considered a useful solution for tasks relating to gathering data on large areas and structures. Any system that contains separate nodes, for example CPUs in a multiprocessor system, can be considered a group control object. Now, to succeed, the S-bots must have a control method for the individual action and strategies for interacting with each other in real time. This can make use of autonomous actions, planning, purposeful changing of the environment, and making purposeful problem-oriented judgments. Ukrainian scientists such as Dodonov, Gorbachik, and Kuznetsova published works showing the difficulty in achieving the most efficient organization of these mobile units. There are many social, natural, and technological systems whose control strategy can serve as an important inspiration for a swarm-bot system. One such strategy has each S-bot in a swarm-bot system making decisions independently after exchanging information with other S-bots, and forming its own strategy based on its history. This approach is known as a herd, and happens when each S-bot fulfills his own task as part of a global mission. Each of the tasks is simple, and the solution of the individual task is optimized, rather than the entire system. Since all S-bots are equal, a loss of one does not compromise the overall mission of the swarm-bot system. Increasing the survivability of the group does not come at any additional cost thanks to the decentralized control arrangement. However, decentralized group control requires difficult algorithms and does not guarantee optimal solutions. These swarm algorithms divide into two types: swarm particle algorithms and ant colony algorithms. And they can solve harder optimization problems. The main challenges are tuning and adaptation to the specific optimization. The selection of the right coefficients is discussed in the works of people such as Dorigo, Kenny, Shi, and Eberhard. Looking at a specific swarm-bot system, we start by setting up the problem. We have a set Z of elements of a set Z of the subtasks and a set B of the S-bots. Next, we need a reward matrix, the reward for completing each subtask by each bot, the cost matrix, which in opposition is the resources spent by each S-bot when completing such a task, and finally a matrix of possibility, linking whether an S-bot can complete one subtask or not. Next, we want to divide the subtasks between the S-bots and solve the global mission Z in a way that maximizes the gain X. Now, the gain is guided by this formula here, which relates the number of the S-bots, the subtasks, the rewards, resources, and the possibility of completion. The results are stored in an array, where each element represents a subtask, and the value of each element represents the number of the S-bot assigned to that task. So, an array of 3, 1, 2 will have S-bot 3 completing the first subtask, S-bot 1 completing the second, and S-bot 2 completing the third. The distribution of subtasks between each S-bot is done with a central particle swarm algorithm. It leads us to a standard deviation of a random I particle, as well as its variance, the mathematical expectation of it, and finally the probability of its appearance, all outlined in the formulas on this page. This leads us to an iterative method. We start with a random swarm initialization, where we have random positions, speeds, and directions. Next, we work out the best local and global solutions based on the total distance between the S-bots and their destinations. And then that takes us to the classical particle swarm algorithm formula, which corrects the position of the S-bots and makes sure they don't venture out of search limits. You can see this formula relates values such as the speed and the position of some random ith particle, as well as the local and global solutions weighted by coefficients, and the best solution determined by a random ith particle, in other words the local optimum, and the best solution among all particles of the set, in other words the global optimum. Now, the last step is to check that the conditions were met, and if they weren't, we go back to iteration number 2. We can now look at the results of the experiment detailed in the paper. First, we have a graph of particles plotted against the root mean square deviation. Next, we can see the number of iterations, also plotted against root mean square deviation. And finally, the number of subtasks compared to the root mean square deviation. This shows us that we can build a centralized particle swarm algorithm in a swarmbot system and successfully solve it. In fact, the developed iteration algorithm is characterized by ease of operation, a small set of input parameters, sufficiently acceptable accuracy, and encouragingly, a fast convergence to making the optimal decision. Some research which could follow this up could be making a genetic centralized algorithm and a comparative analysis of other swarmbot system algorithms to see how they measure up to this one in specific applications.